So my name is Marcel Böhme. I'm tenure track faculty at Max Planck Institute for Security and Privacy in Bochum, and my group is called Software Security. And I'll share my screen so that you can see what I'm doing. Can you see my screen? Perfect. Yeah, excellent. So you see that screen which shows the slides. Okay. All right. So before we go into the lecture itself, I just wanted to talk a little bit about what I do, and maybe that's interesting for you, and maybe you can snooze off for 2 minutes to wait for the actual lecture topic. So what I do is about finding bugs in programs, and you could say trying to make machines attack other machines. And since this is the last lecture in the fuzzing course, I don't actually need to say a lot about this. So some people look at how to make fuzzers faster. And so there are three general topics under this fuzzing for automatic vulnerability discovery, called effectiveness, which is about finding all the bugs in a program. Efficiency, if you have a limited time budget, like every one of us, maximize the number of bugs found within this limited time budget. And scalability is when you have a limited time budget, but a lot of resources, like computational resources. So what happens as you scale the computational resources, but given the same time budget? So people have looked at this. This is the aspect that most people and most researchers in the fuzzing community look at. They develop new techniques to make fuzzers faster, scale better, make them more efficient, find more bugs. But another part of my group, and this is what this lecture is going to be about, is working on quantifying this, quantifying fuzzing, understanding, making predictions, extrapolating. Why is this interesting? Because most people think of testing and fuzzing being the automated version of testing as a process that doesn't give you any guarantees. If you don't find any bugs, what do we know about the security of the software system? So I'm going to talk about this, and this is going to be the main topic in this guest lecture. But what it also allows me to do, this second part of my group, Foundations of Software Security, to look at fundamental limitations that are essentially a problem for all of these techniques, that are fundamental to all techniques. One example of this is scalability. So one of the recent papers that I wrote was establishing that finding bugs comes at an exponential cost. So if you use a fuzzer, using fuzzing for vulnerability discovery requires an exponential cost, and that means exponential number of machines. So, for example, you have a lot of machines. You have, let's say, 10 machines. Then you increase your number of machines to 100 machines, and you find 100 bugs. You increase the number of machines to 1,000 machines, you again find only 100 more bugs. If you increase the 1,000 machines to 10,000 machines, so you go exponentially in terms of your number of machines, you again only find 100 bugs. So an exponential increase in the number of machines gives you only a linear increase in the number of bugs found. So this is what I mean with kind of foundations and limitations. Okay, so also another disclaimer. This is going to be less slides and a little bit more programming. So I'll do live programming, which means I'll probably do something wrong. I need to look up stuff. I'm a little bit prepared, but not, live programming. Sometimes things go wrong, but it's okay. What I want you to focus on if things go wrong is how I correct them. But I hear that Andreas also had a similar approach. So, and this is also thankfully one of the main benefits for the fuzzing book, that you can actually try things differently. And so this is what I really love about the fuzzing book. So what I would like to start with is maybe you can go to the website called polf.com/swsec and answer for me what you think is when we should stop the fuzzer. So I've opened a window here which will quickly reflect this. So the website is this. And if you go there, you have to enter your name, and then you can give an answer. Like, what do you think What do you think? What is the reason why we should stop the fuzzer? Right, so a fuzzer, what it does is it essentially generates a large number of inputs. And so I could generate inputs for an hour, for 12 hours, 24 hours, a month, a year. So there's nothing really holding me back from stopping the fuzzer. But maybe there is a reason why we should stop the fuzzer. Okay, so one response is because my boss tells me. So I also posted the link, so I'll just draw this window above this link. I also posted that link on Zoom, so you can also click on that Zoom link. So when my boss says so, it's very like when your time budget runs out, right? So sometimes you have a boss that gives you computational resources. Sometimes you have a budget on your computational resources. Sometimes you have continuous integration running, and your continuous integration pipeline only allows you to run your fuzzer for an hour. So yeah, time budget is definitely one way of stopping fuzzing, stopping fuzzing. Okay, so the next best response is never stop fuzzing. So if you had unlimited resources, then you would never stop the fuzzer, right? But this is not true either, because fuzzing is something which you do in an incremental manner. So most of the course has probably been about automating the fuzzing process and thinking about this as you develop your program, then you push the button of your fuzzer, and then the fuzzer finds all the bugs, and then you go on developing your program. But that's not how fuzzing works in practice. Often you develop the fuzzer and the fuzz harness, and maybe if you do grammar-based fuzzing, the grammar, and all the artifacts around the fuzzer together with the fuzzer. So you would have to stop fuzzing just to improve your fuzz harness. University explodes is probably never stop fuzzing. When the coverage stagnates, and this is a good way of thinking about progress, a good way of thinking about fuzzing. A fuzzer generates inputs, and then it achieves some kind of coverage. And you also talked about coverage before, or it finds bugs, right? So, but it finds these bugs in the beginning a lot. You achieve a lot of coverage in the beginning, but later on you kind of saturate. And this is what may be meant with when coverage stagnates, when you suddenly don't have a lot of progress anymore. And this is different from one subject to another. Sometimes you have small programs that you want to fuzz for a little bit, and coverage or whatever measure of progress you have quickly saturates, and sometimes you have larger projects where you can fuzz forever, and you never really reach some kind of a plateau. Okay, so so the good answer is, if you had unlimited resources, you can fuzz forever. But things change. Your program changes. You need to rerun the fuzzer. Your test harness change. You need to rerun the fuzzer. And often you're kind of constrained with the money you have for your computational resources and the time you want to spend. But only using time isn't a very good use of your resources. So we'll focus on this response when coverage stagnates. Let's just have a quick look at the other responses. When it's no longer economical, that's of course true. Right, so all code covered, we'll talk about this too. Or time budget runs out. So you won't be able to cover all the code, and we don't know whether we can even cover all the code. I'm going to talk about this in a second too. There's a bearing threshold. Yeah, there's a threshold, and yeah, this is going to go into that discussion about when does my progress, the current progress, kind of stops being good enough, and what good enough is defined by a threshold. Paper deadline is, of course, always a good stopping criterion for your fuzzer. Okay, when you find a bug, of course, it's also like a trivial when you find a bug, you can go and fix it. So, okay, so these are the responses. We'll focus on this progress idea. So you've been running your fuzzer for 24 hours and you found no bugs. And now your question is my program free of bugs? Now, because you didn't find any bugs doesn't mean your program is free of bugs, right? So there's this famous quote by Dijkstra, who said that program testing can be used to show the presence of bugs, but never to show their absence. So that means testing only shows bugs. But what happens if we don't see any bugs? So since 1969, we kind of moved on, and so what I hope to show today is that you can understand fuzzing also as a statistical process, where you think about input generation as a sampling. Yeah, okay. And from this, we can use statistical methods simply to make predictions and quantify certain properties that we're interested in, like what is the probability that the next input that we generate finds a bug? So what is the residual risk that the bug is found if one more input was generated? And this is a practical question. We published a paper on this idea, on residual risk. And so we were approached by companies, including Fuzzbuzz, who said that this is really interesting to them and they would like to know more about it. And here is Justin Campbell, who is main developer of a team that develops OneFuzz. So if you're familiar with large continuous fuzzing platforms, there's OSSFuzz from Google. Microsoft has also been developing large continuous fuzzing platform called OneFuzz. And Justin thinks that this is a really important kind of attribute to have, to understand when kind of there's a situation when we can stop investing more computational resources, stop the fuzzing process, and use these computational resources in a better way. Maybe change the fuzz harness or do something more to find bugs in these programs. So this is the question: when to stop fuzzing, and then when we stop fuzzing, actually go on and make something, use the time for something better. So okay, so what is our model? So we'll use a statistical model, and this model is called a multinomial model. What we're going to do is we're going to draw balls from an urn, and each ball is going to have a color. And so now each ball corresponds to an input that we generate, and the color corresponds to something like a path that is exercised or something like that. So I can't see in that urn. Unlike you, I cannot see. I can only draw from that urn. And my question is, okay, I've drawn 10 balls from that urn. I don't know how many colors there are. I don't know how many balls are in this urn. But I can now see the colors of the balls that I have drawn, the 10 balls that I have in my hand. So maybe there are 10 balls, and maybe I've seen 4 colors. I can now ask the question, what is the probability that I draw one more ball, that I see a color that I have not seen before? And so there are statistical techniques that we're going to discuss today that allow you to answer this question. So here, one problem is that each ball has to have one color, but this model was then extended from an ecology of all domains, where each ball can have more than one colors. So I'm changing the metaphor now. What happened? So in ecology, people are interested in sampling individuals from what they call an assemblage. So suppose you're an ecologist or naturalist. You're interested in the species of bugs in the rainforest. So what they do is they sample individuals, and from the sample they want to make predictions about the species in the rainforest, and they can answer the same question. So this is called the Bernoulli product model. So they extended this. Essentially, each ball can have multiple colors, one or more. And so I use this terminology of species. So then if you've looked at, sorry, if you looked at coverage graphs, you always see this kind of situation. You can ask questions about, when we are at this point in the campaign, what is the probability that we find that we generate an input and we increase coverage, or we can extrapolate. So we are at this point in the campaign. If we invest so much more time, how much more coverage would we achieve? And coverage is just some kind of arbitrary thing that we can put anything up here. It can be the number of species, the number of paths, and the number of branches, and number of assertions violated. The graph will always look the same. Or we can ask questions about this asymptote. Like what is the total number of colors, the total number of species that we can see in the limit? How does this relate to fuzzing? I'll show you now. Okay, so now comes the live programming part. So what I did is I loaded, can you see the VS code? Okay, wonderful. So I loaded fuzzing book infrastructure. So you git clone fuzzing book. And so I can import book utils. And now the first question is, what is a species, or what is a color? The first thing I'll do is I'll create a subject. My subject is a parser, which is an HTML parser. And I define a function called myParser. And it takes an input and simply constructs an object of this type, HTML parser, and we're gonna feed these inputs to the parser. So this is simply a wrapper function. Okay, let's load that. So we loaded that. And what we're gonna do now is if you remember, there was a chapter on coverage, and we are going to import the module, the coverage module. Then we define an input. Since this is an HTML parser, let's just take an HTML tag. And then we are going to execute this wrapper with coverage instrumentation, literally. So it's not instrumentation, but yeah, it's collecting coverage. Okay, so what happens now? Let's check out what it does when we call coverage here. So we see, I don't really care how myParser is implemented, but what I care about is that some statements in that function are covered. So that's good. We have one input called HTML, like open and closing HTML tags, and we execute it, we get some kind of output. Let's just squish this together a little bit. And let's try another one just to see how it works. Do we get another coverage trace? What do you think? So it looks quite different. If we do something like hello, we'll get another one again, much shorter one because it's not really HTML. But because the way the parser works, if I type hello and hello, there shouldn't be really a difference. So let's see. Yeah, it gives you the same trace. Okay, let's try to capture this in. Let's try to capture this. So what we do is instead of this is the Bernoulli product model. Each input can belong to one species. Let's make each input belong to one species. What we do is we construct like a hash over this coverage trace. Okay, so how do we construct the hash? We'll import something called pickle, and we also import something which can compute as the hash function. And then we define a function which takes this coverage object and firstly pickles this for us. So we take this coverage output, the list that we saw before, and pickle it. That's the way for Python to say, you take an object and squish it into a string. If you can unpickle that string and you get the same object back. Okay, so but from this string, we now compute a hash. So we take this hash lab function and compute a MD5 over this pickled curve. And then return the hash curve. Hashed curve. Sorry, hash curve actually. So this is what we return. Let's see what it does. So it compiles or it loads properly, which is good. Now we again take some kind of input. Suppose again our HTML, closing HTML, see what we get, which kind of hash we get. So what we hope is that we get this hello and hello as the same hash, right? Because it would exercise about this, definitely the same coverage. So first we check the trace hash for HTML. This is this. Oh, sorry, we have to text the hex digest for this, and the function, of course. And so this is our hash for this. If we execute it again, you get the same hash, right? So let's try this for hello and hello. We should get the same hash. Okay, so firstly we get a different hash, of course, because it exercises something different than the HTML tag. And now we get hello. And so we get the same hash, which is wonderful. So now the ID for a path can also be the species for an input. This is essentially corresponding to one path. Different inputs can exercise the same path. Symbolic execution, if you remember this, would construct a path constraint for all inputs that satisfy the path condition and exercise the same path. So we, instead of this path condition, we compute this kind of hash. Okay, so now we ask this question: what is the probability that the next input, the next generated input, increases coverage? This is what we are really interested in. And what we start with is we'll import something from the first lecture. So we take a random fuzzer, and if you remember, it has a certain parameters. What we want to do is we want to generate strings of a certain length. And so the min length of that string can be something like 1, and the maximum length is 100. And what we can, okay, so this works for some reason. And I want to generate only characters that are like proper characters. So they start from space and end at tilde. So just for you to verify that, this is the ASCII table and space is here. 32, and we take all the range all the way to 126, which is 32 plus 94. Let's see what it does. Fuzzer fuzz should generate, doesn't do anything. We forgot a comma here. Okay, so this is what it does. It generates these random conjunctions of characters. So now let's create a population. So what we do is A population is like a seed corpus. So we want to generate a lot of inputs now. And later we want to compute the coverage for these inputs. And then we want to compute the probability that the next input we generate increases coverage. Okay, so population is this. It's like an array. And then for, excuse me, for all I in, so for all I in trials, we'll simply append whatever population gives us, whatever the fuzzer gives us. Okay, so this should be good. Let's see what the first 3 elements are. Works, that's good. So we have, this is like the first 3 inputs in this population of 50,000 inputs generated by our simple random fuzzer. Okay, so now we compute coverage. What we do is we take the set called all coverage, and we'll collect coverage information in here. So again, with coverage, maybe I can just copy paste. Right, so that's what we do. With coverage, as coverage, execute my parser on that input. Okay, and then we take that coverage and append it to our all coverage. What we do is, instead of appending it, because it's a set, we union that in. Construct a set, get trace hash, and add this, whatever coverage is in this coverage object, right? And we translate that with get trace hash and append it to all coverage. So what it does is it takes for all inputs in the population and will compute this coverage set. Okay, let's check it out. I won't print it because it's going to be very large. And it won't print. Okay, so now it says something not implemented. And this error actually comes from my parser. So what I'll do is I'll simply ignore, as we do in software engineering, we ignore all errors, except if you're working in cybersecurity, where we are interested in seeing all these errors. So we just ignore all base exception, which is essentially everything. And say ignore means pass. And then it doesn't know base exception. There we go. Okay, so now we compute this coverage. It's going to take a while, but not too long. 5 seconds. That's good. So what we're going to do now is, okay, we have constructed coverage information for this corpus of things. And now we're computing an estimator called Good-Turing estimator. But before we do that, I'll just introduce you to singletons and doubletons. And almost all estimators of these kind of quantities are based on singletons and doubletons. So singletons are just very rarely observed things, like very rarely observed species. In fact, singletons have been observed only once after sampling, in this case, 50,000 inputs. And doubletons, in the same sense, have been observed exactly twice. So, and so the idea in these predictions is often, this estimation is often that things that are very rare predict things that have never been seen. Okay, so how this is, this sounds very vague, but I'm going to explain it using a bit of mathematics later on. Okay, now we have, let's collect our our singletons. We'll just copy paste this down here. So we collect coverage, but in addition to this all coverage, we also collect some singletons. It's going to be a set, just like the other. And it's a little bit tricky, but what I do is first I prepare this. I call a thing called current coverage. And I'll just assign on my set for the current input, the trace hash for the current input to this current coverage. And later on, I'll just do the same. I'll just union current coverage into all coverage. So this keeps track of my coverage stuff. But I also use this current coverage to compute my singletons. So the first trick is a little bit simple. What I do is I take the current coverage and remove it from my singletons. So why can I remove it? If it doesn't exist, nothing happens to that set. If it exists, because I've seen it the second time, right, I can remove it. So that works. Now we have to update singletons. So the trick here is a little bit different. What I do here is I'll take, okay, I'll first find current coverage and intersect that with my all coverage. And then so what it gives me is if this intersection is empty, current coverage has not been seen. If this intersection contains current coverage, it's already been seen at least once. Okay, so then I take current coverage, subtract this set from it, and then union whatever the result of this is into singletons. Okay, does that make sense? So this singletons now contains all the things I've seen only once. If I see the same thing a second time, I remove it. Okay, so let's run that. So it goes through all inputs in the population, it computes this coverage. In addition to this coverage, it computes these singletons. And now we see that the total number of coverage elements that we've seen exactly once is 172. And the elements that we have seen, the total things that we have seen, like the total coverage elements are 443. So definitely less singletons, but quite a high number of singletons too. Okay, so now how do we compute the probability that the next input that we generate belongs to like covers something new? How do we compute that probability? And so there's this, so this question was investigated a very long time back by Alan Turing and his assistant Good. So Good was his assistant, and he actually published this result. Turing didn't really think much of this result, so he didn't publish it himself. But it went on to become one of the most important statistical things, estimators of missing mass. It's actually the most, I'll explain why in a second too. And it works reasonably well. So what we estimate is missing mass is the probability to find something which we have not seen. If we have not seen an event, there's still a probability there that this event might occur in the future. So the estimate is very simple. The estimate is the number of, so we take the string length of the singletons. So this gives us the length of the singletons divided by the number of trials. Okay, this is the estimate. Let's see what it comes out as. 0.0034. Yeah, so how do we know this is right? So what we do now is I just write a quick empirical evaluation of this result. And how do we do this? How do we evaluate the probability that the next input that we generate increases coverage? So what we do is we simply stop the fuzzing campaign at this point, and then simulate continuing this fuzzing campaign for one input, and do this like 10,000 times, or an arbitrary number, and then take the proportion of trials of simulations for which we have seen coverage increase, right? So this is how you would compute this empirically. Okay, so let's get a count, which we set to 0. Then we compute some kind of validation validation test suite, these extra next inputs essentially. So we do this by taking, I take trials again, it could be less, but just to have a number here. And append whatever the fuzzer says. So this is constructing my next inputs. This is my simulation. And now I'm just going through this. Yeah, I actually copy paste this. Try this. Okay. And current coverage is again my set, whatever, I'll just take this again. And now we ask if the intersection of all coverage with my current coverage is 0, then let me just remove these parentheses. If this intersection is 0, then we have seen something new, and we should keep track of it. Okay, good. That sounds good. And now my empirical estimate will be simply the number of things that we do a string again. So we have a string count divided by the number of trials, right? So we generated trials, many inputs in the validation thing, and checked how many of these inputs actually increase coverage on our current all coverage. And this is the count, and this is the number of trials. So this is the result. Let's see what comes out. We hope that this is going to be very close to that. Okay. Okay, it's a problem. Trials. I don't know. Well, let me just print this. Zero is, of course, incorrect. The length of the intersection is 0. If count plus plus. We see what count is. Actually, I can just see what count is without actually rerunning this. Count is 0, which should not be the case. So what is all coverage? Is filled. Okay, so current coverage is set. Inputs are being executed, which is fine. Try. Oh, I forgot to run the parser, of course. Okay. Sorry, with coverage. Yes, coverage. So we don't keep track of coverage, which is bad. Let me do that. Now we should be. So the second number you see will be count divided by trials, which is hopefully our rough estimate. There we go. 0.00354 is the proportion of. So it's the probability that the next input increases coverage empirically, and this is our estimate, right? So 0.00344, and here it is 0.00354. But the difference between here and here is that we had to run the entire fuzzing campaign to make this again, right? To make this estimate, compute this estimate. Only by keeping track of these singletons during the fuzzing campaign, you can already make that statement. You can already estimate the probability of increasing coverage. Okay, so, firstly, why is the probability that the next input increases coverage actually an upper bound on the probability that the next input exposes a bug, right? So we've talked about coverage right now, but what we actually want to make a statement about is the probability of exposing a bug. And maybe I can just quickly flash that EARN model again. So why is that? So we have seen, suppose we have seen purple, red, and blue in our sample. We do not know about yellow, green, and we do not know about, we do not know about yellow and green. And now suppose that one of those colors is one of those inputs, one of those balls, I can just arbitrarily paint black. And that represents an input that reveals a bug. So if the probability that I take a ball out of this urn that corresponds to a color that I have not seen, including the color black, I have not seen a bug yet, gives an upper bound on the probability that the next ball I draw is black. And therefore, the probability that an input, the probability that the next input that I generate increases coverage also upper bounds the probability that the next input that I generate exposes a bug, simply by recoloring these balls. Okay, so how are you doing in terms of time? I think I have 15 minutes left. Okay, so let's do some math. So why does this Good-Turing estimator work so well? That's the question that I would like to answer now. And what I do is I just, whoever is now interested in a little bit of probabilities and maths can follow along. Okay, so what we start with is the probability that, suppose we go back to that urn model. We pick one color. Let's say we pick the color blue for some reason. So PI gives the probability that any ball that I draw, the next ball or any ball that I draw from the urn has the color blue. Okay, this is PI. That's the probability. That's simply the proportion of blue balls in my urn. Okay, so 1 minus this gives me the probability that the ball that I draw is not blue, right? And if I take that to the power of n, you can follow the thing here. Actually, maybe I can increase the, okay, it just went away. There we go. That to the n gives me the probability that after n trials, I have not seen the color ball, the color blue, okay? And if I subtract this from 1, I get the probability that I have seen the color blue after n trials. So this is how we construct that formula. And if we want to do that for all colors, not just the color blue, I'll simply take all the indices for the colors. Suppose we have S colors and they're all numbered from 1 to S. Then this is simply the number of species or the number of colors that I can see after n inputs. Okay, so because it's a sum, I can actually take this one out and I can just say this is this. I think this step might be clear. Okay, so now let's look at delta n. This is the quantity that we've just estimated. This is the probability that the next input that we generate has not been seen. Delta n is actually simply the difference between the number of balls that I've seen after generating n plus 1 inputs, plus the number of balls that I've seen after generating n inputs. Simply that difference, right? So if you look at this graph, I don't know, I can impromptu draw a line here. But yeah, so it's essentially the delta. If this is n and I don't know, do I have a pencil here? Shape, line. Okay. So this is n. This is n plus 1. Then this difference between here and here, this is my delta n. Okay. And so, okay, so let's figure this out. We have Let's just take Sn plus 1 is simply this plus 1 and minus the same. Okay, I have to put parentheses around this, otherwise. Okay, so this is what I get if you see below here. Now you can remove S. You can take the minus minus and turn it into a plus. And you can rearrange that by taking the first negative term and put it after the positive term. So we get this, okay? Because these are sums, we can simply take this. These are all over the same indices. Can simply remove that sign over this sum. So this is mathematically okay. And now let's just factor out this extra 1 minus pi. So we get 1 minus pi. So okay, this is that. And so what we're going to do here is I'm going to show you why F1, this number of singletons divided by the total number of trials n, is a really good estimator of delta n. And you'll see why. It takes a second and you need to follow along, but it's going to be really interesting. So now we unpack this. Okay, so we take this away. Sorry, so 1, and then plus this. Okay, right, so this makes sense, hopefully. So we can take that 1 away. So if you look very carefully, this part can be removed, right? So this is just the same, a minus a is 0. So we remove that. And we are left with that. Okay, so this is finally the thing that we end up with. And now there's something which you need to believe me, which I cannot construct here, which is that the number of singletons is actually n times sum of I equals 1 to the s of pi 1 minus pi to the n minus 1. And that's crazy, right? Which means that F1 is actually n times delta n minus 1. Okay, so what is the estimator for Good-Turing? Good-Turing had developed. So Turing developed and Good then published, or maybe they developed it together. The estimate was delta n equals, sorry. So this we are here, right? So this is the estimate. So we said, take this number of singletons and divide this by the number of trials, which is this really simple estimator. And if you look carefully, you see that this is nothing but delta n minus 1. And this is why it works so well. Okay, so we talked about one estimator, the Good-Turing estimator of the missing mass. How does this relate to fuzzing and when to stop fuzzing? You want to know what the probability is that the next input that you generate exposes a bug. If this, or increases coverage, if your measure of progress is coverage. If your progress drops below a certain threshold, probability is simply too low. You had to generate, you might need to generate 10,000 more test cases to make a little bit more progress. You simply stop the campaign. You have to make some call. And this threshold changes from subject to subject. That's one idea. The other is, instead of looking at when this threshold, when this kind of, you're approaching this asymptote, You could also look at the asymptote itself. You could say, this is what the fuzzing book chapter talks about too, so I'm going to not talk about this here. You could also estimate this asymptote and then say, well, I'm 90% towards the asymptote. And so does it make sense for me now to continue? You can make this decision as well. But you make this decision not because you only have 5 hours left to the deadline, but because you know that you don't have the, because you know that you don't have to make any more progress. You don't make enough progress if you invest more resources.